All right, so today what we're going to be doing is really finishing up talking about improper integrals. So there was one more example of this first type we've been talking about, and then there's this other type of improper integral where rather than having an infinite interval, the issue is that we run up against a vertical asymptote. So before we get to that vertical asymptote type, one thing that we really haven't touched on yet is how do we handle this if we have both of our endpoints infinite? And so when we laid out what these are supposed to mean, a day or so or two ago, what we said was if you're given something like this, pick any point and you really split it into the two types of integrals where only one endpoint is infinite. And you can actually pick any point that you want. Usually, 0 is a good point because it's kind of right in the middle. And also, when you have to do some evaluating of the integrals, having 0 makes things simpler. So the way that we'll understand this is that this is going to be integrating from negative infinity up to 0, 1/1 plus x squared, and then the integral from 0 to infinity of 1/1 plus x squared dx. And writing it like this kind of implicitly says, if either of these diverges, the whole thing diverges. But if we get a number both times, then we actually add that up. And a choice that I'll make in evaluating this is I'll actually do both of these all at once. You could decide to write them separately, but what you'll see then is the work is basically the same, so you can maybe compress things a little bit by just doing the two separate tracks at the same time, and they're really similar work, so you really only have to think about these things once. So the first step is these are both actually limits. They're different kinds of limits, because this first one, we're taking the limit as t goes to minus infinity of the integral from t up to 0 of 1/1 plus x squared. And then what I'm going to do, I'm going to say, because these are really different limits, and I want to make sure I'm thinking of them separately, I'm going to say, pick a different letter s and let that go to infinity. And I'm going to integrate from 0 up to s of 1/1 plus x squared dx. Not because anything is actually going to be different, but just we're treating these as different limits. And although a lot of the work will be the same, this will maybe just help me keep track of what's what, just in case it matters and we don't want things to get mixed up. So we write each of them as limits, then we have to integrate this. This limit, or this integral, is actually one that we know. 1/1 plus x squared is inverse tangent. And since it's the same function both times, both of them will become inverse tangent, or arctangent. So this first one, we still have the limit. The integral is inverse tangent. We're going to minus infinity of, we'll say, arctangent of x. And we're evaluating this from t that will take a limit of up to 0. And then secondly, it's the same function, so it's the same integral. But we're going to take the limit as s goes to positive infinity of arctangent of x, going from 0 up to s. And the next step, evaluate these things in. So our first one, we're taking the limit as t goes to minus infinity of arctangent of 0 minus arctangent of t, and then plus our second limit, which is the limit as s is going to infinity of arctangent of s minus arctangent of 0. And right here, this is where I think the value of picking a different letter here shows up, because we really do want to look at this and say these are two halves. They both have to separately be convergent. And if it was all t in here, you might be enticed or something to see an arctangent and an arctangent, and you might cancel those out. And that you really don't want that cancellation. We want to make sure that whatever this limit is doing is the value of this improper integral, and the right limit is this improper integral, and they both have to exist on their own. But now we can evaluate this. And one thing in this case, or this example, which hasn't really showed up, is the limit of arctangent, which we'll have to really do twice. It exists, but it's not just 0. A lot of the other times we've done these integrals, what's happened is the function part either goes to infinity or doesn't exist, or it goes to 0 and we're just left with the number that we have there. That's not always how it works, and you want to be on the lookout for that. So remembering what arctangent looks like, pulling this out, arctangent is this sideways tangent, which is something like this. So it does have these vertical asymptotes, but they're up at pi over 2 and down at negative pi over 2. So when we have to evaluate these two limits, this is the picture that we need to have in mind. Also, I guess what this graph can point out is at 0, arctangent is 0. So those numbers turn out to be 0. And in this case, we're sort of flipped. The limits are what gives us a finite number. So this is 0 minus, if we're going to minus infinity out to the left, we get negative pi over 2. And then here we're going out to the right, so we're going to positive pi over 2 minus 0. And those negatives cancel. Pi over 2 plus pi over 2, which means we actually get exactly pi. And this function, just so we have a picture of it, is something like this. So this shape has exactly an area of pi beneath it. Which is kind of surprising and maybe appropriate because Sunday is Pi Day, which is great. Questions about this problem? The new thing is we kind of split it down the middle, but we really are, once we split it, treating it like these kinds of limits that we found before. Before moving on to something totally different, as a brief aside, as another way of looking at this is that won't get us to this answer, but another way to kind of analyze these integrals would be that x squared plus 1 is bigger than x squared because it has a plus 1 on it, okay? If we flip these fractions, 1 over x plus 1 is less than 1 over x squared. That's how fractions work. If you have bigger things, 5 is bigger than 2, and when we flip it, 1 over 5 is smaller than 1 over 2. That's how fractions work. And then actually what you can say is, the last time we talked about comparing improper integrals. So since the integral of 1 over infinity, or 1 to infinity, 1 over x squared converges, last time we talked about these p integrals, and if this p is bigger than 1, then it converges. And it turns out that this is bigger than this function. So we can say that the integral from 1 to infinity of 1 over x squared plus 1 also converges. So that says this area here, if we start at 1, we know there's a finite amount of area there. And going to 0 is finitely many more area. So we can really, without actually doing any integrals at all, figure out that this integral converges. But it doesn't get you this pi over 2, which is the drawback. So there's the second type of integral. Which is what happens if you run up against a vertical asymptote. And having spent a while thinking about this kind of limit, there's a maybe natural thing that we do. We just have to figure out what is the right limit that lets us handle this vertical asymptote. So for instance, if this is maybe 1 over x, and we want to find this area here. So this is from 0 to 1. What we would want to think about is how can we use a limit to let us only ever actually be doing definite integrals that over intervals where this thing is continuous, but then using this limit, let us get all of this area. And the idea is, well, we can't go all the way up to 0, but we can get really close to it. If we said, let's decide to cut it off here, and this area is something that we can find, because we're not going up against an asymptote. We have a finite interval where it's all continuous, and so that's okay. And then say, well, we're still missing a little bit of area here. So what if we move a little bit closer? And now we're getting all of the blue stuff plus all of this extra green part right here. That's still a finite area, and we're closer to the whole thing because we've inched our left endpoint closer to the vertical asymptote. And then the limit phrasing comes up, and you say, well, if I get closer and closer, if I get closer to the edge of infinity here, then I'm getting more and more of the area, and if I take a limit, then I'll get the whole area. So that's the way that we'll approach this. The limit is saying let your endpoint get closer and closer to where the asymptote is, and then you take a limit of those points there. So this is our type 2. This one would be if the function has an asymptote at, say, A, but is continuous on all intervals that look like A, comma, B. So this, on sort of all of them, yeah. So continuous on A, comma, B. So that's this situation here where B is 1 and A is 0. There's a problem at 0, but if you just don't include that, it's fine everywhere else. Then in this case, the integral that we want, up here, this would be the integral from 0 to 1 of our function, is going to be where we'll take the limit as t goes to A from the right. So we're getting, so that's this, t is this place where we cut it off, and it's getting closer to 0, and we're always to the right of 0, inching back in towards 0 here. And then we're integrating from that t, that place very close to the asymptote, but not there yet, up to B, the endpoint where there isn't a problem and we don't have to mess with, and we're integrating the function. So that's how we'll handle this. And the relevant of this plus means, well, if you were allowed to be on the other side of your asymptote, then that would be like looking at a point over here, getting closer to 0, but that includes the asymptote, and that's the whole issue. So we need to make sure we stay on the side of the asymptote where the area is, but get closer and closer to the asymptote, and then take a limit. There's also the case where what if the asymptote is on the other side, which has the same sort of look to it. So if we have some function f has an asymptote at B, but is continuous on, so including A and everything up to that asymptote, but not at the asymptote. Then the way that we'll do this is the integral from A to B of our function is now take the limit as t goes to B from the left. And we're integrating from A, the endpoint where things are fine, up to t, which isn't quite at the asymptote, but is getting closer to it, of f of x dx. And this would be like taking this picture and flipping it. So we would want to go not all the way up to the asymptote, so just up to some t, but let that point where we stop get closer to the asymptote. So what would this look like if we actually tried it? So what is this area here? So what is the integral from 0 to 1 of 1 over x dx? And right here, we see something kind of deceptive. The other kind of integral, there was an infinity there just smacking you in the face, and it says, I'm definitely improper because you have an infinite amount of area. This one looks innocuous. It's just the two numbers, oh, great, a finite interval. So what you need to check, and especially for the next exam, have this in mind. You can think, why would Dr. Adams give me this integral? I should make sure it's not improper or something like that. And in this case, you would look and say 0, domain issue, that's where the asymptote is. So that's where I have to take a limit of. So since 0 is the limit, or 0 is the asymptote, we're going to take the limit as t goes to 0. But because our interval looks like 0 to 1, the t's that we want to cut it off at are going to be inside this interval. So they're places like over here, which are all to the right of 0. So we're approaching 0 from the right. And then we have our integral from t up to 1 over x dx. Once we get this written down, it has a very similar feel. We have to do an integral, we have to do a limit, but slightly different kind of limit. But before we finish off this problem, are there questions, either the specific example or the general way that we're approaching this other type of improper integral? So then, if we're on board, let's do this. So integrating 1 over x, we can't use the power rule. This is the one non-power rule case. So here we actually get the natural log of x. And we're evaluating this from t up to 1. Then substitute these in. And this is what we'll actually take a limit of. So the limit as t goes to 0 from the right, the natural log of 1 minus the natural log of t. And now we'll need to remember, well, what happens in this second limit? So what happens to the natural log as you get closer and closer to 0? And at 0, the natural log actually has a vertical asymptote. So the natural log has this shape. We are looking at the limit as we go to 0 from the right. So we're heading down this asymptote. So this limit is actually the natural log of 1 is 0. So that goes away. But since we have this infinity, we aren't really going to worry too much about the number because this whole thing is infinity. So this area is infinite. So asymptote lets us get some finite, or over this finite interval, we're able to go vertically and get this infinite amount of area. Questions about this problem? We'll see some more and some kind of different ways of approaching this and different things that can happen. So let's try one coming from the other way. So let's evaluate this integral, 0 to 64, 1 over the square root of 64 minus x dx. So in this case, again, we look at this and say, well, they're numbers. Given the context of this course, there is probably going to be an asymptote somewhere. And this time it's at the top point. If you put in 0, the bottom is the square root of 64, that's 8, that's fine. But now if we put in 64, the top end point, then we get 0 in the bottom, and that says that we have an asymptote here. So now we're in this case where we have an asymptote at the right end point of our interval. So we still want this to be a limit, but now we're going to take the limit as t goes to 64, where the asymptote is, and we're coming from the left. Because now we have our interval 0 to 64. The bad part's on the right end point, so we want to back up a little bit just below 64, and then work our way back towards it to accumulate all of that area. So now we're integrating from 0 up to t, 1 over the square root of 64 minus x dx. And this one's a little more complicated. So, sometimes when we're integrating these, when you get to this step, you do what you've got to do and integrate that. So let me space here. So in this case, you can potentially eyeball this if you see what happens to all of the constants, but the safest way would be do a small u substitution. It'll be pretty quick if you do it. But what happens is u is going to be inside the square root. So that's 64 minus x. Take a derivative, the constant goes away, we get just the negative. We move the negative around. And so what we're actually integrating, and I'll keep up working on the side here, doing the full u substitution. And once we know the antiderivative, will come back here. So what we're actually integrating is -1, so a negative shows up. The square root of u, because what's inside the square root, that got all hidden in u. And this is a power rule problem now. So that's u to the -1/2. Write that as a negative exponent. And if you use the power rule with a -1/2 there, what we get is the negative is still there. A 2 shows up because we divide by 1/2. And that 1/2 is the new exponent that we get. So then the last step is putting this u in, but now we know what that antiderivative is going to be. Let's circle back and say we want that antiderivative, and we're going to put it inside this improper integral process here. So we still have the limit as t goes to 64 from the left. the antiderivative is now -2, and I'll put the square root back, square root of 64 minus x. And this is the thing we're evaluating from 0 up to t. So if that integral is not just use an integral rule and you're done, if it takes a little more work, the way that I would recommend doing it is at this point, break off and do the integral, and then say, well, now I can come back and I know that antiderivative, and don't try to make it a lot of things equal to each other. Just say, I'm going to do the work off to the side where I can see it, I being me, the person grading it, and then I'll use it in this chain of things that are equal to each other. But now we can take a limit of this, or we can do the first thing, evaluating at these 2 points. So the limit as t goes to 64 from the left of -2 square root of 64 minus t, kind of linked together, minus t there, then minus this thing with 0 in the middle, which if we put 0 in, we don't get this minus x. So we get plus 2 the square root of 64. And then this simplifies to be pretty nice. When we find this limit, this thing is actually continuous. So we can just put 64 into that square root, and we get square root of 64 minus 64, that's 0. The whole first term goes away. And the square root of 64 is 8. So this time, this does converge, and it converges to 16. Questions about this part? Either specific steps or how it all hangs together, or why these are the steps that we need to connect to find this integral. So let's look at something else, and I'm not going to really tell you what the first step is, but we'll want to think about how do we start approaching this, keeping in mind that it's in the middle of a lecture about improper integrals, so that's the sort of thing we need to be looking for. So what about -4 raised to or up to 0, and 1 over x plus 3 dx. So the questions with this are, why is this in the middle of today's class? And what is different than the examples we've done? And then lastly, what do we do about it? So what are some answers to really any of those questions? So it does have an asymptote. What's different about this one as compared to the other examples?
The asymptote's on that one, or about.
Yeah, so in this case, there is an asymptote, and given a rational function, what you're looking for is where's that denominator 0? Well, if x plus 3 is 0, that's at -3. that is in the middle of this interval. So this is saying find the area between -4 and 0, but within that stretch, we have -3, and there's an asymptote. And if there's an asymptote in the middle, how do we think we want to deal with that? So we haven't really said. Yeah, so what the two examples we've done have said, if your asymptote is an endpoint, then we've seen these are the kinds of limits you write down. So the way that we'll deal with this is say, identify -3 is the asymptote. And if we split it up, -4 to that asymptote -3, and then starting on the other side, -3 up to 0, then this is two types of, or separately, these are at least, they have the same improperness, or they're improper in the same way as the two integrals that we did. And then actually like that first example, looking at this, what we can think is because the steps will essentially happen in parallel, just at the place where we evaluate, the numbers are a little bit different. We can do these at the same time. And actually, so you could do them at the same time. In this case, I'm going to not do them at the same time. And part of it's because I know what's going to happen, but also this 1/x+3, if you have an idea of what the graph looks like, from the perspective of transforming functions. So 1/x+3 is 1/x shifted left 3. So this +3 in there, and when you go from 1/x to 1/x+3, that has the effect of shifting the graph to left, which, among other things, means instead of the asymptote being at 0, it's now at -3. And a thought that you could have, which will streamline things a little bit, is we actually just did 1/x, and we saw that it diverged when you tried to find the area along the asymptote. And if this is basically the same thing, then it should also diverge. We're still going to check it, but the thought process is, if I think this is going to diverge, if I check just one of these and check and see that it diverges, then the whole thing diverges. So if you place your bet that I think this is going to diverge, you can just do one of them, and if you get that infinity out, then you win. You know that it's going to diverge. If you're wrong, though, and you get a number out, then you say, well, now I have to go do the other side, and it might be really similar, but that's some more work you have to do. So in this case, seeing the relationship between that this is similar to 1/x, if you think it's going to diverge, let's just check one of them. And we'll see that this does actually diverge. And we can pick maybe either one of these. This one has a 0, so that's kind of nice. So let's try just this one. So now -3 is the asymptote. That's the thing that that we use in our limit. And so this is the limit as t, we're going to -3. And since the interval here is all to the right of this, we want to be to the right of -3. And this is from t, our cutoff before the asymptote, up to 0 of 1 over x plus 3 dx. And then we can integrate this. In this case, you can do a small u substitution, but in this case, there's actually no constant at all. So if you do that u substitution, you'll be able to just replace this thing with u with no extra constants. The end result that I'll just jump to is when you integrate this, you get the natural log of x plus 3. And this is what we're evaluating from 0 to t. So this is what we get to put in, or we put in these two endpoints. So we're going from, t is going to -3, and we're looking at the natural log of 3 if we put in 0, minus the natural log of t plus 3. And what really emphasizes that this is really kind of the same thing as 1 over x. If you look back at that 1 over x example we did, this is almost exactly where we were, but now there's 3's, or I guess this is, instead of, there's some more 3's around. This is a 3 where it used to be a 0, and that 3 wasn't there. There was just a natural log. But anyway, so it is really similar, but we'll just do this one on its own. And now what we're doing is the natural log of 3 is fixed, but if we try to put in -3 here, what we get is this natural log of 0 thing, which isn't a number, but is saying that what is happening is as t is going to -3, the inside of our natural log is going to 0. And what happens if you put things going to 0 inside a natural log? And what happens is that the natural log has an asymptote right there. So the natural log of x on its own, as we had before, has this asymptote at 0. The natural log of t plus 3 also has an asymptote, but it's at this -3 that you hit. So this natural log of 0 form is not a number because you can't put 0 into a natural log, but this is infinity because how we interpret this is what is the natural log doing as you go to 0, and it's going along its asymptote down to -infinity. So this is like we're taking the limit as x goes to 0 from the right of the natural log of x, is how we think about something like that. And that's what we wanted to know. So what we did was this first integral is that it has an asymptote in the middle, we'll split it up into 2 pieces. By checking one piece and seeing that it diverged, that's the whole thing. We just actually don't even have to worry about this because the conclusion is this improper integral diverges because one of the halves diverged. Questions about this, or really any of these problems, any questions that have been sort of accumulating, or as we see more examples, if there's something about them that you don't quite, or hasn't quite clicked or you don't quite like. What can we do? This is the 5 minutes. Okay. The last thing is kind of a long example. Let me do just one more of a different type, just to keep seeing things that are a little bit different. So let's say the integral from zero to pi over 2 of tangent. So something like this. If this showed up on an exam, your calculus senses start tingling. Why would I get an integral like this? What's the problem? And the big problem, since it's not difficult integration-wise, maybe you don't remember exactly what it is. Maybe you need to look up what tangent is, but it's on our formula sheet. So the thing is this thing improper? And this one actually is, because tangent is looking something like this, where it has these vertical asymptotes everywhere, and this shape keeps repeating. So at pi over 2, this actually does have an asymptote. So we need part of is being knowing where these asymptotes show up. And when it's rational functions, you're really looking for where's the bottom equal to 0. For things like tangent, it's really knowing what the graph looks like. But once we've identified this is a vertical asymptote at pi over 2, we can get into our group. We're going to pi over 2. Are we approaching this from the left or right? The left. So either graphically we're saying the asymptote is here. We want to be just a little bit off to the side, and then so we can move back towards that asymptote as we take a limit. So we're taking the limit from the left, integrating from 0 up to t of tangent. We might have to remember what the integral of tangent is, but if you check that, we're still taking a limit, pi over 2 from the left. This is the natural log of secant, going from 0 up to t. Stuff those things in, evaluate. Limit as t goes to pi over 2 from the left. The natural log of secant of t minus the natural log of the secant of 0. So as trig problems kind of do, the calculus steps are very similar to what we've been doing before, but there's this extra layer of knowing what these trig functions do. And what might be the best way is, in all of this case, thinking of secant as 1 over cosine. So what happens if we are looking at, the big thing is this first one. What happens if we're letting t go to pi over 2 from the left of 1 over cosine of t? Then we have to think, well, cosine of pi over 2 is 0. And that says that we have a vertical asymptote. And then check, is this positive or negative? If we're putting in things a little less than pi over 2, so seeing what pi over 2 is, maybe cutting off a few decimals, what you'll check is that we're actually getting positive numbers here. Or graphically, cosine is looking like this. This is pi over 2, and to the left of it, cosine is positive. So whatever's happening, the form of this limit is the thing inside the natural log is going to infinity. And secant of 0 is 1 over cosine of 0, that's 1. But what we see here is that this expression, natural log of infinity, isn't a number, but what it's saying is what happens to the natural log as the thing inside it goes to infinity. And the limit as x goes to infinity of the natural log, so the thing inside is going to infinity, this is also infinity. Because putting up one last time, the natural log has this graph, but now instead of saying we're going along this vertical asymptote, we're going out this way and it keeps getting bigger and bigger. So this graph also happens to have an infinite amount of area, but well, we've at least seen something that doesn't, but we really have to check every time. Okay, so starting next week, we're going to be talking about different applications of integrals that'll be using some of these improper integrals and some techniques of integration, but seeing what it can be used for. All right, have a good weekend. Let's see you next week.